let's get started.
1 minute.
1 minute?
No, sorry.
Yeah. All right, so I'll be talking about El Nino conditions in the equatorial Pacific in 2014 and Hurricane Patricia in the northeastern tropical Pacific, which formed in October 2015. Patricia was a very interesting hurricane, and it really seemed kind of out of place in the eastern Pacific. You'd expect to see something like this threatening the Philippines or the other islands in the western Pacific, where the ocean conditions are and the atmospheric conditions are much more favorable for this kind of storm. So we're interested in what the upper ocean anomalies, the conditions in 2015 that might have contributed to this extremely intense hurricane in the eastern Pacific. And this shows images near the peak of the intensity of Hurricane Patricia, infrared and visible satellite images. So in general, 2015 was a very active year in the eastern Pacific. This shows the tracks of all of the tropical cyclones during that year, color-coded by intensity. And I've circled Patricia in the far eastern Pacific. So this was kind of a unique hurricane, actually, because it had a pretty short lifetime, and yet it achieved a very high intensity. And it was actually of all these storms that formed, it was the only one that was a Category 5. And you might say it was the El Nino conditions developing in 2015, but we also had a very strong El Nino developing in 1997, and yet there's a lot less activity overall in the eastern Pacific. So there was something else going on in 2015 that led to this active season and possibly Patricia. Okay, so just a quick summary of the 2015 season overall. 26 named storms, which was second only to 1992, 16 hurricanes, 11 major hurricanes. These are both records in the eastern Pacific. The accumulated cyclone energy, this is just the sum of the squares of the maximum wind speed of each storm along its track. This was second only to 1992. And predictions, they're predicting an above normal season in terms of activity, but nowhere near what actually occurred in 2015. So this keeps with the interesting aspects of the season. And so the ocean anomalies, surface anomalies are shown here for October 2015. The top is the SST anomaly in 2015. The middle is 1997. And you can see the developing El Nino in both years. The unique thing about 2015 was the above normal SSTs outside of the equatorial band in the Pacific, extending into the tropical North Pacific. This didn't really occur in 1997. And this region is where we had most of the activity in 2015, the bottom plot there, over this warmer than normal SST. The bottom left plot shows the sea level anomaly leading up to October, this July. And they show above normal sea surface height throughout the equatorial Pacific, and also notably in the northeastern tropical Pacific, the region where Patricia was. Okay, so there's a recent paper just came out, and they looked at the causes of the activity in the western development region of the eastern Pacific. So it's the boxed region in the lower plots. And they showed that it was mainly record warm sea surface temperatures, and they related it to El Nino in the Pacific meridional mode. Mid-level humidity, mid-level humidity and low-level vorticity also contributed, and also reduction to record low vertical wind shear in the central part of the basin. And the bottom plot there shows this wind shear anomaly. And you notice that to the east of this box, there's actually above normal wind shear, or close to normal. So this doesn't appear to have played a major factor in the region where Patricia was. So there must be something else. And the recent study shows that the subsurface ocean can play a big role in the Eastern Pacific in terms of the seasonal activity. This shows the temperature in the ocean averaged from the surface to 105 meters. The top is for kind of a composite when you have low subsurface temperature, and the bottom is when you have high subsurface temperature. So what happens is during an El Nino, the heat builds up on the equator, and then at a lag of a few months, several months, it propagates and reflects into Rossby waves and deepens the thermocline in the northeastern tropical Pacific. And you can see the enhanced values of temperature, upper ocean heat content in this region, and then the tracks of the hurricanes during each of these different phases. So a lot more activity when you have the high subsurface temperature, because you're giving more heat content and you're reducing the cold wakes of the storms, enhancing the intensity that way. The blue contours are the 26-degree isotherm. So there's not much change in the SST. They're arguing it's really the subsurface temperature that can have a big impact on the hurricane activity on seasonal timescales. And so that was kind of a broad overview of the season and the large-scale conditions. I'll focus mainly on Patricia in this talk, and the track is shown here. So it had a pretty short lifetime, but achieved very high intensity. It was actually the most intense hurricane in the Western Hemisphere, and it was second only to Typhoon Tip, a Western Pacific super typhoon, in terms of central pressure. It had the highest recorded sustained winds ever, 213 miles an hour, and it was a very rapid intensification from 85 to 205 miles per hour in only 24 hours. And it actually decreased in intensity a lot before it made landfall, but was still the most intense hurricane to make landfall in Mexico. So another interesting aspect of Patricia is that the intensity predictions were really bad. They were some of the worst that the Hurricane Center has ever had in terms of the official forecast. So this, I've reproduced them here, the yellow bar on the right of each plot. So this is the average forecast error of each storm going back to 1988. And the really thing that stands out about Patricia is it consistently has very, very high forecast errors across all lead times. No other storm has had such a pronounced error across all. Yeah.
Question, you mean the most intense in the Pacific side? Because for Mexico, January 1955 easily eclipses at landfall. Patricia.
So you're saying there's a more intense landfalling hurricane? Ah, okay. You might be right. Maybe the Pacific, yeah. Yeah, okay. Yeah. Okay. I see. Okay. So there's a stronger one on the Atlantic side that made landfall.
Oh, yeah.
Yeah. All right. So I'll modify that. The most intense to make landfall on the west coast of Mexico. Okay. All right. So the predictions were very bad, adding some intrigue also to this. And for the rest of the talk, I'll look in more detail at the ocean conditions in 2015. I'll do a long track analysis for Patricia, looking at possible causes of the changes in intensity. And this will be mainly the variation of the potential intensity formulation. And then the causes of the 2015 anomalies in October, focusing mainly on sea surface temperature and sea surface height, explaining those anomalies. So this shows the anomalies of SST and sea surface height in the top two panels during October 2015 when Patricia formed and made landfall. You see a lot of red in the SST plot, and it's really actually a minimum in the anomaly where Patricia was. It had the strong developing El Nino on the equator, and then this other meridional mode type pattern up to the north. But still 1 to 2 degree warm anomalies in the region where Patricia was. Sea surface height was also at record levels, record highs in the region where Patricia was. And the surface salinity, so this is the actual surface salinity, not anomalies. You can see the ITCZ expression here, the low salinity. And interestingly, there was a big decrease in salinity along Patricia's track as it made its way to Mexico. Okay, so this is looking at the subsurface. That was surface plots. This is subsurface ocean temperature in October 2015 on the left. And I've also included the depth of the 26-degree isotherm. The climatological value is red, and then for 1997 is white, and 2015 is black. So there's a bigger than normal pool, deeper than normal pool of warm water at the time of Patricia passed through this region. And the SSTs, again, they're close to 30 degrees along the track. And in terms of anomalies, you can see the big warming in the subsurface, this deepening of the thermocline relative to 97, and also the climatology on the bottom. And this would have helped to reduce the cold wake and enhance Patricia's intensity. And looking at salinity, so this is the satellite salinity in the left plot from the SMOS satellite sensor. And these surface salinity values agree well with the GODIS surface salinity, which we use for the analysis, because it has the subsurface data. You can see the decrease in salinity along the track of Patricia. So this is going from the start down here at the south along the track to the last location in the north. And this increased salinity stratification here, especially in the upper 50 meters as Patricia went through. And the salinity signal, it shows up, it's not caused by the storm itself. This shows up before Patricia even formed, the first 3 weeks of October. The average is shown here, the satellite data. And it's there in the climatology. It's a little less pronounced, but there's also this decrease in salinity. And it's not due to rainfall. Rainfall is actually below normal. The lower right plot shows that. So the most likely cause is river outflow. There are two big rivers in this region, the Rio Grande de Santiago and the Balsas. Come out at about 18 north and 22 north, and there's sediment. You can see sediments and chlorophyll as the rivers come out into the ocean, and they'll produce a low salinity signal also. So that's what we think is causing this low salinity toward the end of Patricia's track. All right, so there's some evidence that there were some pretty significant anomalies when Patricia was making its way toward Mexico. And the next thing we want to do is try to quantify the impact of these anomalies on the intensity of the hurricane. So we use the potential intensity formulation. So this is kind of the Carnot engine cycle is what how you can think of it. So this is the most efficient way that you can transfer heat energy into work. So in this case, we're taking heat from the ocean and we're transferring it into the winds of the hurricane. So the heat here is coming from this enthalpy flux, latent plus sensible heat fluxes into the atmosphere. And it's also proportional to the difference in temperature, the SST minus the outflow temperature up high in the atmosphere. That affects the efficiency. And then it's scaled by the enthalpy exchange coefficient and the drag coefficient. So with this, it gives the maximum theoretical wind speed that a hurricane can achieve given the environmental conditions and the air-sea flux of enthalpy at the surface. But this uses SST. This is SST out ahead of the storm, and then actually the storm induces a cold wake, and that's going to decrease the SST that the storm feels. So we want to modify the SST to something more realistic for what the hurricane actually felt as it passed over a given region. And to do this, we'll define a dynamic temperature, is what we'll call it, and it's just the temperature in the ocean averaged from the surface to a mixing length L. And for example, if the storm is stronger, it's going to mix deeper, so have a larger value of L, and this will give a lower value of temperature than if you have less mixing, a weaker storm. And that'll be the more realistic temperature that's felt by the storm. So we need to find this L to average over vertically. And we use basic scaling, Monin-Overkopf theory. So it's this mixing length is this proportional to the friction velocity, the wind speed of the storm, and divided by the turbulent density flux. We can't, of course, calculate this turbulent density flux, so we need to parameterize it. And we'll say this W prime can be approximated as this final mixing depth induced by the storm at a given location minus the initial mixed layer depth out ahead of the storm divided by the time over which this mixing acts, T. So that's W prime, and then the rho prime is the change in density going from the base of the mixed layer initially, mixing down to get to the final mixing length. That's delta rho. And one more thing is to assume a linear increase in density between the base of the initial mixed layer and the final mixing length. And then we can solve analytically and get an expression for this final mixing length as the storm passes and mixes down. The initial mixed layer depth plus this term proportional to the wind friction velocity cubed, the time over which the mixing acts, and the density stratification below the mixed layer, alpha. We take the maximum wind speed of the storm to calculate U star at a given 6-hour location. And then to get T, we use the actual translation speed and a radius of 8 kilometers. This was a very small storm, Patricia was, so it only had about an 8-kilometer radius of maximum winds. And alpha, we get this from the GODES subsurface temperature and salinity. Calculate the stratification. And then we can use this mixing length to calculate an estimate of the SST felt by the storm as it passes a certain location. And we can use this. Well, first we did some validation. We ran a 1D mixed layer model, PWP model, and we found pretty good agreement. Correlation is about 0.8. This is using a variety of different stratification, stratification, wind speed, and translation speeds for storms. And running this the numerical model and comparing it, the correlation is about 0.8, and there's no significant bias. And we also looked at the observed cold wake for Patricia in black and the estimate based on our formula, which is the red. And you see both show this increase in the magnitude of the cold wake as Patricia intensifies. Our method underestimates it, and this is probably because we're considering only the cooling that affects the storm, so only in that first radius of maximum winds as it passes by, whereas the observed cold wake from satellite data is really taking the whole cold wake after the whole storm goes by. So we're interested really in the SST that the storm feels and how that's affected by the ocean conditions out ahead of the storm. Okay, so we have some confidence in this dynamic temperature formulation. We can now plug it into this potential intensity equation. This is, again, giving the maximum theoretical wind speed that a hurricane can achieve, and we'll call it the dynamic potential intensity. This shows scatter plots of the actual intensification rate on the y-axis and our dynamic potential intensity on the x-axis here, and explains about 30% of the variance in the actual intensification rates in the Eastern Pacific. This is going back to 1998, looking at all storms up until 2014, and it does much better than other formulations. This is taking just a 0 to 100 average for temperature, and this explains none of the variance, 0% of the variance, and using the traditional SSTPI explains a lot less, about 12% of the variance. So this seems to be an improvement over other methods. Okay, so then we have this formula, and we can do some sensitivity studies with it. We can swap in different subsurface temperature and salinity and see how it affects the cold wake and see how it affects the potential intensity of the storm. And we do kind of a control, you could call it a control experiment, where we just take 2015 temperature and salinity from GODES, as well as the atmospheric state from 2015. And then we test the impact of subsurface temperature. We swap in the 1997 temperature and atmospheric state, keeping salinity the same. And then we do another experiment looking at the climatological subsurface temperature and keeping the 2015 salinity. And finally, just set salinity to a constant and look at the effect of this decrease in salinity along the track on the potential intensity. So that's what we will look at. So this shows these different experiments looking at the cold wake. So the first thing to notice is that this, although it intensified up to about more than 200 mile per hour winds, this is the gray bars here showing the intensity. The cold wake really was only around 1 degree, which is pretty small considering the intensity of the storm. So this 2015 ocean conditions is blue, and then if we swap in the 1997 subsurface temperature, we get a larger cold wake and an even larger cold wake if we swap in the climatological subsurface temperature. So this is saying that there was this additional anomalous warming and deepening of the thermocline in 2015 significantly reduced the cold wake as Patricia went by. And the right shows the anomalies. So taking the cold wake using 2015 conditions and then subtracting the cold wake using either the climatology or the 1997 conditions, and showing at least a 0.5 degree decrease in the magnitude of the cold wake if you use climatology or 1997. And the salinity effect is shown in purple. So there could have been a reduction of about 1 degree Celsius based on this decrease in salinity, increased salinity stratification as Patricia approached Mexico. And this is consistent with the warming, subsurface warming along the track. And then we can use this in the dynamic potential intensity, look at how the intensity might have changed based on this. And we see significant reductions in potential intensity if we use the 1997 or the climatological subsurface temperature. So the conditions were much more conducive to intensification because of the subsurface temperature anomalies in 2015 is what this says. And this is mainly due to the SST anomaly at the beginning, and then the reduction in cold wake plays a bigger role toward the end of the track. Okay, so then the right again shows the differences between using the 2015 conditions and the other conditions, and it shows increases in the potential intensity of about 10 meters per second, and due to the salinity is also can be close to 10 meters per second. So possibly about 20 meters per second increase in intensity due to the combination of the mean salinity decreasing and the anomalous subsurface temperature in 2015. All right, so if you look closely, you'll notice that the actual intensity for the last location here is about 95 meters per second, and the potential intensity, the maximum theoretical wind speed, is less. It's about a little more than 75 meters per second, and you see a decrease in the potential intensity as the actual intensity goes up. And we think this is due to a bias in the SST. We use the NOAA OISST monthly data, and if we look at the microwave satellite data, it shows warmer SSTs along the track of up to 1 degree. And if you consider this would increase the potential intensity, and it suggests that maybe our analysis is actually underestimating the strength of the anomalies in 2015 and the impact on Hurricane Patricia. And the climatologies agree pretty well. So it's mainly these anomalies that we think might be underestimated using our method. So another possibility, you might say, well, the atmosphere may have contributed because that's included in the potential intensity through the atmosphere, the near surface enthalpy and the outflow temperature down in this equation. So we looked at the DPI, the potential intensity, the enthalpy flux, which agrees well with the potential intensity, and the dynamic temperature, the estimate of the SST felt by the storm. And it's really driven mainly so that this SST is driving the enthalpy, which then is driving the potential intensity. And the outflow temperature really has hardly any effect on Patricia's potential intensity. So it really is the ocean, the change in the SST and the change in the cold wake amplitude that's driving it. Okay, so what caused the record high SST, sea level, and deep thermocline in the northeastern tropical Pacific? I showed that these upper ocean conditions seem to have had a big impact on at least on the potential intensity by deepening the thermocline, increasing SST. So we want to know what caused these anomalies. Okay, so this is just global maps of sea surface temperature anomalies starting in winter of 2014 going through July 2015. And so there are a couple of interesting features here. One is this blob, the warm SST blob in the North Pacific in the winter of 2014. And then by the summer of 2014, the lower left plot, the blob is persisting in the North Pacific, and we're starting to get a warming signal in the equatorial Pacific. And this led a lot of predictions to say that there was going to be a big El Nino in the winter of 2014-15, which turns out never happened, looking at the upper right plot. Now the anomalies seem to be going away. Going into July 2015, however, there would seem to be a resurgence of the warming in the North Pacific and kind of the extension to the southeast along where the region where Patricia was. And also in the Eastern Pacific, we started to get this big warming leading up to the very strong El Nino in 2015 and 16. So the question is, was the warming in the region where Patricia was it caused by this North Pacific warm blob kind of migrating southward into the northeastern tropical Pacific, or was it the ENSO influence? Was it the El Nino warming that ended up warming up, deepening the thermocline in the northeastern tropical Pacific? So that's the question we want to answer. And if we look at kind of the standard thing with El Nino, you look at longitude time plots along the equator. So the left plot is sea surface height anomaly along the equator. This is the bottom box in the plot on the right, going from the date line. The left side of it is the date line, and the right is near the coast of South America. And so in the left plot, you can see this eastward propagation of positive sea level anomalies. These are the Kelvin waves. They're generated by westerly wind anomalies near the date line in the Pacific. The contours in the left plot are the zonal wind anomalies. So these high sea surface height signals propagating to the east, and then is interrupted by actually an easterly wind anomaly event in July 2014. This kind of halted the development of the El Nino, and then it resumed. You get additional westerly wind anomalies and eastward propagating Kelvin waves, which continue to deepen the thermocline and all the way through 2015. So there's really kind of a long buildup to this El Nino in 2015. And then the middle panel shows the SST anomaly in the northeastern Pacific region, the top box on the right panel. And you can see reflection. So the longitude axis has been reversed, so you can see reflection at the boundary and then propagating westward, radiating as Rossby waves as these Kelvin waves turn into coastal Kelvin waves and then radiate westward in the northeastern Pacific. And there's also Ekman pumping, local Ekman pumping, tending to deepen the thermocline, the positive Ekman pumping anomalies, especially July through October 2015. So it does appear that El Nino, at least on sea level, had a big impact in the region where Patricia was. And this is consistent kind of with a canonical impact from El Nino. So this is the same kind of plot looking at observed sea level. In the middle, it shows along the equator, and you can see the eastward propagating signal and then turning into these westward propagating Rossby waves in the northeastern tropical Pacific. And this is due to the seasonal or the anomalous north-south movement of the ITCZ associated with El Nino warming. And it causes wind stress curl in the northeastern tropical Pacific, which deepens the thermocline, and also the reflected planetary waves. So it's consistent. 2015 is consistent with this idea. All right. So, but the 2014-15 development of the El Nino was really pretty unique, and it's mainly because it took so long to develop. It was such prolonged warming in the equatorial Pacific compared to other events. Normally you see a peak. So this left plot here shows all of the El Ninos going back several decades in the Pacific, and they generally peak in the winter, and then several months before, or a year before at least, they're either neutral or negative La Nina conditions. And in 2014 and 15, There were positive anomalies going back at least a year, even more, and this was very unique. The only other case was 86-87, but the peak in 86-87 was much smaller compared to 2015, the red dot. So this was really unique in terms of the duration and the amplitude of the El Nino event in 2014 and 15. And then the right plots here just show the anomalies, the Nino 3.4 anomalies for 2014-15 and 96-97, showing persistently warmer SSTs at the beginning of the event, going back a couple years in 2014-15, and also for sea surface height, even though they reached about the same level in October, near the peaks of the events. And this had significant impacts on the northeastern tropical Pacific. So SST was much higher than compared to the 96-97 time period. Sea surface height was persistently a lot higher compared to the earlier event, and Ekman pumping was stronger, tending to deepen the thermocline more. And this is averaged in this boxed region, the Patricia region here. Okay, so the next question. So this is saying that the El Nino looks like it forced the sea surface height anomalies, but what caused the SST anomalies was it linked to the SST anomalies in this northeastern Pacific region. And that's the next question. So why was the SST so much higher in the northeastern tropical Pacific compared to 97, October 97? And to look at this, we use the mixed layer temperature budget. So we can express changes in SST in terms of the surface heat flux, and we found the latent and the shortwave fluxes were most important. The others, long wave and sensible, were not as important for the heat budget. Horizontal advection of temperature and vertical turbulent mixing at the base of the mixed layer. The SST change, we used the monthly NOAA optimally interpolated SST, surface fluxes and horizontal advection, the trop flux product, which uses satellite and ERA interim data, the Oscar currents for horizontal advection, as well as the OISST gradients, and vertical turbulent mixing is estimated as the residual from these other terms because we can't estimate it or calculate it directly. So this shows the mixed layer temperature budget. This is averaged in this boxed region shown on the left where Patricia was. The top shows the surface heat fluxes. So overall, the change in SST, this is the anomaly relative to 96-97. The change in SST is kind of a very small signal compared to the surface heat fluxes. The dashed lines show the latent in blue and the shortwave in red. And this is using a constant mixed layer depth, so no mixed layer depth anomalies are included in this. And then when we include the actual mixed layer depths from 2014-15 and 96-97, we get the solid lines. So the mixed layer depth was a lot larger, a lot thicker mixed layer in 2014 and 15 compared to 96-97. So this really diluted the impact of the heat flux on the SST. The heat capacity increased, so you get relative cooling, anomalous cooling in 2014-15 due to this thicker mixed layer, even though the actual surface, it just enhances the anomalous cooling, and the latent heat flux has a slight opposite effect because in the mean the latent heat flux is cooling, so you get slight anomalous warming when the mixed layer is deeper. Okay, so this can't really explain the maintaining the anomalously warm SST. The horizontal advection, you see some warming here from the meridional term, and this is mainly this southeastward advection of the warm SSTs from this meridional mode and the warm blob type signature in the North Pacific. But it's a lot weaker compared to the surface flux signal. It's about 0.2, whereas the surface flux, the shortwave is cooling by up to 4 degrees per month. So this is not the main This is not the main way that the Patricia region was warming relative to 96, 97. And so if we take the residual, we see a big anomalous warming, the black line, and it has an interesting structure to it. We think this is related to the mean changes in thermocline depth. So seasonally, there tends to be a reduction or a shoaling of the thermocline, and then an increase in thermocline depth when the values are positive, so the axis is reversed here. So you get a shoaling. When you get a mean shoaling, this means that anomalies can have a bigger impact on the rate of cooling. If you have a mean deepening, even if you have an anomaly, you're not going to get any change because you're still going to have the same rate of cooling. So it's really acting on this seasonal cycle. You tend to get the highest anomalous warming when you have the highest mean shoaling of the thermocline. And so it appears that it was really the El Nino. It really was the buildup along the equator, the sea level thermocline depth deepening along the equator as this El Nino developed, and then this heat content being taken eastward and reflecting into Rossby waves and deepening the thermocline in the northeastern tropical Pacific. And this deepened the thermocline, reduced the vertical mixing of temperature, and led to an anomalous warming and maintained that really high level of SST in 2014-15, leading up to Patricia's arrival. Okay, so this just shows the mixed layer depth from the GODES product. 2014-15 is the red, and then comparing to 96-97, and the climatology for the 2-year periods. So much thicker than normal mixed layer depth is what the red line is showing. 30 to 35 meters in 2015, late 2015, summer, fall 2015, and 15 to 25 meters only for climatology in 96, 97. So this played a big role in actually causing cooling, anomalous cooling from the surface heat flux to even damp the warming induced by the ocean effects. Okay, so summary. So we found that upper ocean conditions likely significantly aided the intensification of Hurricane Patricia in the eastern Pacific. This was through a deepening of the thermocline, record warm SST, and also the mean salinity decreasing along Patricia's track. The effect was to increase the stratification and to decrease the mixing, the cold wake induced by Patricia, which increased its potential intensity, the energy available to extract from the ocean. The warmer SSTs we found were caused mainly by a deeper thermocline, and these were induced by the prolonged El Nino conditions in 2014 and peaking in late 2015. So this deepened the thermocline and reduced the cooling from vertical mixing, maintaining the high SSTs. So there are a few papers. The first one is the main. This is in press describing in more detail what I presented, and then the second one describes the method, this dynamic potential intensity method, and then this also uses a similar method in looking at salinity in the Western Pacific on global warming timescales and its impact on tropical cyclones. So, okay, I have a couple minutes, so I can't resist asking the question, why were predictions so bad of Patricia? And I don't know the answer. I'm not, I'm not an expert on prediction or atmospheric processes, other atmospheric processes that might have played a role. I really only looked at the ocean, and I think it'd be a good thing to do to look at the atmospheric side of it to see what was going on in more detail. But I can, just superficially, we can look at wind shear. So there were big variations in wind shear along the track of Patricia that you can see here. So The blue, if we just focus on the blue line, there was actually above normal wind shear for this period when Patricia was intensifying rapidly. It went from 86 to 213 miles an hour, and the wind shear was slightly above normal compared to the climatology shown in red. And then when it had this period of rapid decrease in intensity, the wind shear got really high and much higher than climatology. So I think this rapid decrease in intensity likely was caused in large part by the increase in wind shear. And then the question is, did the models incorporate this wind shear correctly? And if not, that could have been a cause of error. So that's why I think that's one possibility, given the large variations in wind shear along the track. Another possibility, salinity, maybe this could have played a role toward the end of Patricia's track. There was significantly more salinity stratification toward the end as it got into this fresh region, which we think was due to the river outflow in that area. And hurricane prediction models, of course, don't explicitly account for salinity in the upper ocean, so this could have been a cause of some of the error in the predictions. So yeah, so I mean that could have been another factor that deserves more attention in general, in my opinion, looking at salinity effects. So I will end it there and take questions.
Yes, just a comment. The couple prediction model, the H-core couple prediction model, and also GFDL have been initialized. They've initialized in the ocean for climatology. Mm-hmm. So they would not have the warm ocean conditions nor the salinity anomaly there. And AMC has not yet looked directly at Patricia, but they've done cases now for Blanca early in the season, realistic ocean versus climatology. And that can account for part of maybe one or two categories. Yeah. But there's still a large gap in the Patricia areas that must be accounted for by the other conditions you mentioned.
Yeah. Yeah. Okay. Yeah. Yeah.
Well, you know, I'm a cloud physicist, okay? So, first of all, salt in the ocean pretty much stays in the ocean, except for what little bit gets thrown into the atmosphere and creates aerosols that clouds can ingest. That being said, however, hurricane dynamics doesn't use salt. I mean, so why would salinity have any effect at all? If it was totally fresh out there, it wouldn't make any difference. I think the temperature of the water is the most important thing.
Yeah, I agree. I agree. Yeah, so I agree that temperature is most important. I'm not going to argue with you about that. What I'm saying is that salinity affects the stratification in the upper ocean. That affects the rate of turbulent vertical mixing in the ocean, which brings up cooler water from underneath. So for temperature, you have two effects, right? You have, if you increase the temperature stratification, you increase the ability, or you increase the cold wake, basically, because you're mixing up colder water, right? But on the other hand, you increase the stratification, which is going to tend to limit the amount of mixing because it's more strongly stratified, more of a potential energy barrier to mix up the denser water, right? But with salinity, you don't have that. You don't have both effects. You only have the increase in stratification. So you put this fresh layer, you're mixing up saltier water, which is decreasing the rate of cooling because you're not mixing up as much cold water, but you're not increasing the cold wake at all, right? So the only effect the salinity can have by adding it is to increase or to decrease the magnitude of the cold wake. So that's the mechanism.
One thing that I would say about your last question, why were the models so bad with the intensity for rapid intensification, is because generally they are that bad.
Yeah.
You know, predicting rapid intensification is basically almost not impossible, but it's really difficult.
Yeah, I agree.
So generally they're that bad. So Patricia's not unique. Another thing is that what makes Patricia interesting case is because we had the hurricane hunters at the same time that it was doing this. but I will put other Eastern Pacific hurricanes that I wouldn't say that they're stronger than Patricia, of course, but I wouldn't say that they're not as strong than Patricia. Simply, we didn't have hurricane hunters there. At the time, it was just basically satellite. So, yeah, Patricia's an interesting case, but all of this talk that is the strongest thing ever, that's just because you have some hurricane hunters there, the time that is doing that.
Okay, yeah, I agree.
Satellites have, they allow you to do certain.
Yeah, I mean, the qualification is strongest and recorded, so, yeah.
I will say that the ADT from Chris Melvin, at the time of peak intensity, that was the highest intensity from ADT from satellite, regardless of the aircraft. So by that metric, Patricia was the most intense in the satellite database.
So Greg, I just had a question about, you were proposing more of an oceanic mechanism between the 2014 El Nino and the warming in the Patricia region, but I know there have been some studies that have shown atmospheric teleconnections between the warming that was experienced there, and so I just didn't know if you'd explore that, whether there was some atmospheric reason for the warming coming from the western equatorial Pacific teleconnection.
Yeah, I mean, our heat budget really showed the surface heat flux couldn't explain it. So if it was some kind of teleconnection that affected the winds, which affected the thermocline depth, I guess, that could be a possibility. But in terms of kind of direct atmospheric forcing, I don't think that was a big part. It seemed to be mainly the oceanic waves, the Kelvin waves, and reflecting into radiating as Rossby waves in the northeastern tropical Pacific seemed to be it. Yeah. Okay, thanks.
What about the paper by Pepe Jean?